So we've eaten lunch and we listened to our presentation. So what I like to do is a little Jedi Master mind trick. You will enjoy my presentation. You will understand the future of refrigerants when I'm done. And you and you will wake up refreshed and ready for the third presentation from Glenn. So, let's talk about the future of refrigerants. It's something very dear to my heart. I've been working on refrigerants for 25 years. And I was hired back in '92 to work on the last transition. And so I was a young pup back then. I'm a little older now. We're going through another transition. And we'll talk a little bit about the challenges in this transition versus the last transition. And we're still fighting those challenges right now. And you did a great job of queuing up the various challenges we have, but I'm just going to start with giving a little plug to Ingersoll Rand and Train. We've been on a sustainability journey for 7 years. We're really high up in the Dow Jones Sustainability Index, and one of the reasons we are is we believe in business and people and society working together for as good toward the environment. And so we have a climate commitment that we work on every day where we're trying to reduce our greenhouse gases by 50% through refrigerants and energy efficiency. But also, we like to make our words and our feet work together. We also reduce our greenhouse gases in our operations. And we work on investing in that too. So a lot of people like to say we're going to invest $500 million in the next 5 years. I like to say we like to invest $500 million in the next 5 years. A little bit bigger number, but they're the same, right? So I think a lot of people, and I give a lot of talks on refrigerants, and I think one of the big areas, people don't remember the history of refrigerants. And so I'm going to give you a little background because I think the history teaches us what the future may hold and what the challenges may be. So back in the beginning, you know, people aren't that old here, but this is before we understood what atoms were, right? So people were taking distillants and stuff off of processes and saying, oh, it had this boiling point, and we were using whatever worked, right? We're cutting ice out of lakes in Wisconsin and using that ice to cool places. So there were very limited applications. There wasn't a lot of mechanical engineers around to design compressors and heat exchangers and do all this stuff. But a lot of these things were either toxic, poor efficiency, high pressure, hydrocarbons, highly flammable, but they were things off industrial processes we were trying to use. And then in the 1930s, a guy came along, Thomas Midgley and group, and he understood that you could take these molecules, pop the hydrogens off them, since they make them flammable, and put chlorines and fluorines and bromines and iodines on them, and you can create designer molecules. And we created CFCs, and this led to the exponential expansion of refrigerants. And so we had a suite of new designer molecules, R11, R12, R22, R502, for the various applications we needed. We also carried along ammonia with us because ammonia is a very efficient refrigerant, like shown on the chart. So where you could use it in safe applications for on the toxicity and the flammability, it still works really well today even. So you'll see it be carried through here. And then we discovered we were, with chemicals in the atmosphere, destroying the ozone layer. And so in the last transition, this is where I come into the picture as a young engineer, is we needed new molecules that didn't have chlorines on them or bromines or iodines on them that depleted the ozone. But the one interesting feature of the CFCs we weren't aware of at the time is they had very long atmospheric lives. That's how they got into the upper atmosphere. And they also cause high global warming as well, which we didn't understand at the time. In fact, a large portion of the global warming occurring from chlorinated materials is coming from R11, R12, and today, and R502, not from the HFCs yet, because they're not high enough at concentrations in the atmosphere. And so we were able to preserve our safety, which was flammability, which was the big thing Midgley was after in the beginning. He was after flammability and suppressing it. And so we were able to preserve that. We were blending flammable refrigerants with non-flammable refrigerants and came up with a whole new suite of new refrigerants. Well, unbeknownst to us, even though we cut the global warming potential of R11 from 14,000 down to some 1,300 for 134A is still unacceptable. And so we're in this transition driving our GWPs the global warming piece of it now, to atmospheric lives that are in days, not in months or in years. I'd say months, tens of years in some cases. And now we're offered safety and design challenges because the molecules are getting more and more complex. They're not so simple anymore. They're 2, 3, 4 carbons long, lots of fluorines. Can be hydrocarbons we have to address. And so now we're looking back at the old chemistries and the old applications. Now that we're more sophisticated, we're looking at hydrocarbons, carbon dioxide, still looking at ammonia, but now we're looking at this whole new suite of chemicals that are out there. So society keeps demanding innovation and innovation changes, which is good for the industry because it continues for us to evolve and incorporate new efficiency, new products, new ways of looking at things. So part of the reason why I'm standing here today is there are phase down of HFCs proposed. And so back in October, after 4, 5, 6 years of countries arguing, we finally have an agreement, global agreement. US has not approved of that, and we're still waiting on that. But the Kigali Agreement on the Montreal Protocol calls for establishing a baseline of what your HFC use, and that's roughly around 2,000 GWP on average, and we're going to talk about averages here by country. Different countries have different averages, but in the US it's around 2,000, in Europe it's around 2,000. And that includes refrigerants that are higher global warming than that, and that includes refrigerants that are low global warming potential than that. And currently there's a law in place in the European Union called the F-gas law, and that's the phase down schedule. They have what was agreed to by the developed countries. You can see like the US, Mexico, Canada, and Japan, and other countries, Australia, that they're following a very similar phase down. This is the minimum you have to hit. You end up in the same spot, which is the important thing to note here, about the same time. It may be a little more aggressive depending on which countries and what refrigerants you mostly use, but you'll end up in essentially the same spot. Now in the developed countries, in the last transition we only had one type of developing country. Now we have 2 groups. There's a phase down there and a phase down for a smaller group of them as well, but they all end up in the same spot. So what's important to know in the bottom line here is that the final GWP baseline to get about 15% is around 300 GWP. So you're going to have things lower, you can have things higher, but it's really a phase down, not a phase out. So in the last program we pulled chemicals and said you can't use them anymore. Here we're looking for how we're going to phase down chemicals. So we have choices, which is really good from an equipment supplier. The regulators allowing us to have that innovation ability rather than tying your hands behind your back. We're able to actually choose and pick and choose about how to get there and meet those requirements. So here's our toolbox. I always like to talk about the toolbox. So as a chemist myself, you have this toolbox of things you can play with and blend them. And the new ones here are in the blue and the red that mostly been added here were the ultra low GWPs and the different concerns around their various refrigerants. And what you see quickly, you see these little flame signals. Symbols around a lot of these where you actually have refrigerants that are flammable. In this transition, when something's stable and it's non-flammable, it's stable in the atmosphere, typically a raise of GWP. Now, they're not all that way. There are a number of refrigerants that are non-flammable in this transition, designated by nothing here next to these, like 1233ZD. In the market, which is already in the marketplace as well, but these are non-flammable refrigerants. So this is the suite of chemicals, including the fluorinated, non-fluorinated material chemicals, as well as blending them with higher GWP materials to help with their attributes around safety. So when you're looking at designing refrigerants, you have a lot of attributes to choose from, and the previous speaker talked about them: compressor discharge and temperature, lubricant selection, refrigerant costs, compressors, and cycles. And so we're trying to balance all of these. As a technology person like myself, and working with various teams, we're balancing all these by application. And the biggest issue here, though, is really around flammability in this transition. And so this is really what's caused the industry to stop and hold and struggling with the transition, is to trying to get these materials and handling the flammability and safety while balancing the cost of the equipment as well as the sustainability of the equipment. So this is a chart that I know Dick has too as well, and everybody presents that. If you look along here, this is the capacity of the refrigerant. Everything's based on a capacity to 134A in this case, and then global warming potential is here. Anything with a square that's blue is a non-flammable refrigerant, and you can quickly see, here's R32 for calibration, here's 410A. 404A is up here somewhere on the ceiling because it's had a really high GWP. But you can quickly see that there's a non-flammable and a flammable boundary that occurs if you want to get down to, like I was saying here earlier, if you want to get down to a 300 GWP, you can see it's possible, but there's a number of flammable refrigerants that we'd have to deal with today. But people are using these refrigerants today. I mean, you can get down to 600 GWP with a 134A replacement. A classic one that's out there is 513A. 404A, there's a number of them out there, get around about 1,200. But with 410A, there are no non-flammable alternatives that are moderate GWP at this point, so you don't see a lot of products being introduced. You do see R32 being introduced. You see a 452B being introduced in small charge products, and we'll talk about flammability here in a second. So here's the classic ASHRAE classification of materials. The important thing you have to remember, there's A and B toxicity, and they're both really non-toxic materials. I mean, these are really safe materials to work with. And then we have, it shows 4 classes, but what the industry has learned is really only 2 classes of refrigerant. There are non-flammable refrigerants, and then there are flammable refrigerants. And, you know, and flammable is what I've learned from the industry research we've been doing over the last 12 months. Once you ignite something, they burn. And they can burn quite robustly, some faster, some slower, but in the end, they are all flammable. And then these lines that are placed here are placed there by man. And I can explain those limits to you, and somebody will say, well, there really wasn't a really good engineering reason for that. And I said, you're right. Class 3 refrigerants are the hydrocarbons. There's only one material as a 2, which sets the boundary, 152A. And then the rest of these material 12s have lower burning velocities, and the number was picked. 10 seemed like a good round number, so we picked 10. And so 10 centimeters per second. And so we have flammables and non-flammables, and the industry has always been fat, dumb, and happy using class 1 refrigerants, whether it's an A or a B, mostly A's, for equipment like this, so you don't really have to think about what you're doing. So it just happened to be, just for this conference here and this affiliates, I wrote an ASHRAE journal article, and it came out this month. And so if you want to know more about flammability, no, I didn't actually, it's just for tourists, this happened. But if you want to go to the ASHRAE journal, I just wrote a paper on flammability new refrigerants options. Mainly talks about the fundamentals of what I've talked here so far, but in more detail. So feel free to look that up. So let's look at identifying the flammability risks of refrigerants. So we talk about equipment, and we focus on equipment all the time, but really it's the whole process that is really what we have to look at. So we look at when the refrigerant's manufactured, when it's transported to the factory, when the factory has to incorporate it into the product. Then we have to deliver it and install it, and then it has to operate. And so the industry's spent a lot of time here around product operation. And then we have service and further either installations or other installations around there with other products, you know, air handlers and things like that. And then we have end of life. And so a leak can occur at any part of the operation. And so flammability risks have to be a cradle to grave understanding. And I'm going to bring in here a new term, and what the industry is trying to do is we're trying to develop flammable refrigerant safety for dummies. And so we're developing the book around that, trying to understand that. And so for people who really don't understand HVAC equipment, I'm sure everybody does here, the biggest risk is charge size, how much refrigerant, how much fuel you have, is it in a contained space, and do you have an ignition source by you? And whatever mitigation actions you may take. So you have the fuel, which is the refrigerant. You have the ignition source of the energy, and once you get that, if you have those come together, you get an ignition event. And we have to understand what the severity of that event is as well. So I always like to describe the severity event as you have a nuclear bomb and a guy has a hammer and he's pounding on it, right? The probability that event occurs is very low, but the severity of the event is very high. Right, if it would go off. So what the industry has done is we went through and we did a risk assessment through all the equipment, and we said, oh yeah, probabilities are low, but some of these charges are really high. Let's go take a look at the severity event. What we found out is the severities can be quite high if the mitigations don't work or the charge sizes are too large. And so the industry right now is struggling with that, and there are standards coming out with proposed and comments on the larger charge equipment. And we also have to worry about the service personnel, in this case, about a Lego guy. But so we have these people today who don't even think twice about handling refrigerants. They go on the roof, they carry their cylinders around. I got my hose, I throw them in the back of the truck, right? They're banging around back there. Truck's contained. Today, we have non-flammable refrigerants. You can be as cavalier as you want. Tomorrow, we're not going to have to be very cavalier. We're going to have trained people. You have to understand those risks, and you're going to run into problems if we're not careful. So how do you control flammability? Well, the first thing you can do is just control the fuel, or reduce the amount of charge. Industry's been working on it for years to reduce the amount of refrigerant charges. There are various systems you can use. For example, I'm assuming this is a rooftop application in this building, or is it? Do you guys know? It's a split system. So, I mean, there's different ways to reduce the refrigerant charge, right? You could split the systems up into many splits. You could create a chiller system, right? And the refrigerant's outside, right? So there's different ways to cut that animal to get the refrigerant either out of the space or reduce the amount of charge or put it in a different situation. Now, there are also ignition sources, and what the industry has been looking at is restricting them or enclosing them, but we can only do the product. We can't control the ignition sources back here in the kitchen, people smoking, people doing operations like they shouldn't be. Like my son the other day, he was building a radio for his class, and he's up there. I'm like, first of all, I thought he's gonna burn my house down as he puts holes in my table, soldering and stuff like that, and I'm like, you know, well, doesn't seem like that's a great thing to be doing if you have a refrigerant around. But we've been designing refrigerants with stronger and stronger ignition energies to get them to get started. So if you think about paper versus logs, think of some of the refrigerants are like logs and big sticks. They're hard to get ignited. Once they get started, they burn. Then we've been looking at severity events. So we've been looking at, do we have to create venting in applications? Do we have to minimize secondary issues to minimize those things? Do you have to prevent operations that are occurring? But of course, lower burning velocity is always better as we get that way. So we've been working really hard on this. It's a large challenge. There's many people in this room that spend countless hours, and sometimes I wonder, I get off phone calls on the research and I have a headache and I'm going, this is really not easy. So back to flammability safety for dummies is use a non-flammable refrigerant. It's really easy. So let's take a look at this. So you have these two events that can occur: fuel with the ignition, that's the probability of the event, and then you look at the severity event. So when you're looking at a chart of risk, you have the different operations that may occur and what the leak likelihood might be. And once you reach about 10 to the minus 8th, it's near zero. But then you have different severity of events. No damage is always acceptable. And so for today, if somebody's brazing on something today and he has a little refrigerant leak, it doesn't matter. If you're using a non-flammable refrigerant, even though the frequency's high, it's always acceptable. But as we move to the right and we have higher severity events, we have to either accept them with caution, accept them with controls, or you just ban them outright, or put them in a situation where you can control it all. So if you look at non-flammable refrigerants, the charge limits are set by the toxicity. So you'll see in a chart here shortly how high these levels can be. They can be very high, and people, the risk of refrigerants today is asphyxiation. I mean, it does occur occasionally, but the safety record for non-flammables is very good. So we're working on a lot of work. It's not well understood at this point, but we're getting better at it. But we're still trying to write that book. So here's one of my only charts in this presentation. On this axis over here, we have the lower flammability limit, and then we have increasing refrigerant charge. And then I have marked the LFL at 100%. So if you reach the lower flammability limit and you have an ignition source, you can get an event. And then I put the RCL up here, the refrigerant concentration limit for 404A in respect to this. And this 308 is basically what 32 and 452B are, all the other refrigerants here. You can see the various refrigerant concentration limits for these materials today, the non-flammables. But you can see here these smaller numbers, these are the safety factors that are put in place in standard 34, a safety factor of 4 to 1. And so you can see these levels would be down here somewhere. So when you start looking at applications, and I started doing some calculations, if you look at portable units, and today, units are sold today with flammable refrigerants and portables. So I kind of took a clause and said this is what the charge would be. And so you have a really small charge. Yeah, you're up on the scale a little bit. But you have that safety margin here in case of issues that occur. And you take automobiles. I took a Dodge Durango, calculated the inside volume of it. It's not this much refrigerant in it. Well, believe it or not, autos are about 50% of the LFL in that cab. And so the industry has found that to be acceptable, still small charge equipment. And then this is where the complexation occurs in HVAC equipment. I'm not going to cover refrigeration much here, but each load in a building is required to meet various applications. And so I wrote a nice paper on this in the Gustafson Lorenzen conference last year, and you can pull that out of literature. But each, residentials have lower loads, offices have bigger loads. You need more refrigerant to do a kilowatt. Dining's a little higher. I would call this a dining type situation, and then commercial kitchens back there are quite high. And then you can have, multiple split units like a VRF system, which can dump into one office because they're connected, and you can end up with, pretty close to the LFL. And this accounts for complete mixing. Now, these things are a lot more complex than they look because, residential might serve a big area, but it might be all concentrated in one spot. It may dump out of a duct somewhere, and then you can lead to an event, so it's not well mixed. So it looks relatively safe, but it's a lot more complex than it looks. And so then we look at public transportation. Here's a bus cabin. It's right at the LFL. Much higher charges. You look at rail, which is interesting. Rail in the saloon area is where the driver is. It's quite high. There's quite a lot of load there. But in the cabin, it's much different than a cabin on a bus. And then we start moving into refrigeration. Think of mobile refrigeration in our Thermo King business. You look at the boxes filled with a certain amount of space already occupied. And so with a trailer, you're already at the LFL. And if you look at a multi-temp trailer where you're using a lot more refrigerant and you're doing multiple zones within a trailer, you can be above the LFL. So these are challenges we don't understand at this point in those applications. So in these applications that are close to line, non-flammability is the way to go for now. Down here, the industry is working really hard on these things and trying to understand how close to that line we can get. And of course, then we have chillers, and they're off the chart here. I just calculated a 750-ton chiller. You might be 800% of the LFL based on an equipment room. So mechanical equipment rooms, you have detectors, you have ventilation, you have requirements for those, you have control of the ignition sources, and so today, if you put flammables up here, the requirements are being worked on there as well. And then, of course, you got special applications like compressed air that are dryers on there. Do you really want to put a flammable into a compressed air system? Thinking that's probably not advisable at this point. So cooling load, space volume, space fill, impact, of course, and assessing that risk. So here's the same chart again. I'm going to throw some molecules up here. Look fancy here. You got YF, ZD, ZE, 600A, isobutane. We have blends of flammable and non-flammable together, 514A, 290 here. So you see these small packaged products down here, and these are products that are being introduced today. So very small charge systems, less than 150 grams for hydrocarbons, less than a kilogram for A2Ls. In the US, products are being introduced. You can go down to the Home Depots, you can go down to Lowe's stores and find these products today. You also see large charge systems, air-cooled systems in Europe being introduced around A2Ls. Of course, in between, there's a large of lower GWP, moderate GWP materials, but not low GWP. And in the large charge systems that are in mechanical equipment rooms, we have non-flammable refrigerants available, so they're being introduced. So when you see a refrigerant get developed that's non-flammable, it gets introduced because it can get past the requirements of flammability. So what's the future look like? I think right now, these are the limits that are set, and people are introducing products. So in the low pressure area, there's 1233ZD that's being introduced, non-flammable for large water-cooled chillers, 514A. You see some ZE being introduced in equipment rooms as well in Europe, not in the United States yet. With 134A, you see a lot of people introducing 513A, which has a lower GWP, and it's nearly a design-compatible material. You see lots of activity in the stationary refrigeration market and industrial refrigeration market, rolling the GWP down to 12 to 1400. And then with 410A, you see 32 being introduced and 452B introduced. But I think the key here to remember for everybody in the audience, innovation is always going on. Don't underestimate the power of people to invent new things. 2 years ago, if you had asked me, were there any new chemistries, I'd say no. And Mark McGlendon completed his NIST study and said there are new things. Guess what? Just because something's eliminated because one factor or another doesn't make man or a woman be able to figure out a way to make it work, and you see that happening every day. So I just caution everybody in the room, the story's not finally written yet. It'll be written in my lifetime, hopefully, before I retire. But not until then, like maybe 6 months before. So flammability is the biggest technical challenge. So a lot of these refrigerants, you have similar COPs and they have similar design issues, but they're all trade-offs. You can design an effective product to any of these. So working really hard there. I think what you already see developing is you have new design center lines that are developing. So in a marketplace with like 410A served from small products to very large products, you see fragmentation. You see hydrocarbons in portables. You see 32 in portables and small charge systems. You see in large charge systems, you see different things happening. So one refrigerant covering the whole gamut may not exist in the future. We've been so used to like R22 doing everything for us in air conditioning, 410A doing everything for us. It took a little while and Dick knows this, it took a little while for the industry to swallow 410A and use it because it wasn't what we really wanted to use. We had to redesign the whole equipment. It takes a lot of time to do that. It was a higher pressure gas. We'd prefer to have something that was design compatible to the existing platforms. So we're going to get a lot of new center lines, and you're going to see a lot of fragmentation that occurs in the marketplace. So you might see a different refrigerant in the ice maker that makes a lot of noise, and you may see a different refrigerant in the stationary refrigeration market. You'll see a different refrigerant in a transport refrigeration unit, because it might have to be non-flammable over there. It could be flammable in that little device. May need low glide in that device versus you can tolerate glide, temperature glide in a stationary refrigeration system. So there'll be different fragmentation that occurs. We just won't use 404A for all these things. We won't just use 410A for all these things. So that's all I have.
Okay, next we have Glenn Gallagher.